About myself, I'm S. Amit Raj, Assistant Professor, EEE Department, Amet University. Now, I am going to discuss the topic induction motor construction and the principle of operation. Now, the first one, the objective of our topic today. The first objective is to understand the types of construction of induction motor, and our second objective is to understand the principle of operation of induction motor. These two objectives we are going to discuss one by one. Now, see the simple constructional overview of our induction motor diagram. Now, before going to discuss our construction, some introduction about our induction motor. These induction motors are mainly used for agricultural pump sets. 99% of our application will affect our induction motors. The three-phase induction motors are the most common and frequently encountered machine in industry. Because of these advantages, what are the advantages? Simple design, more rigid in construction. The price is very low, we know, and the maintenance is very easy. The machine is available from low power to high power. Different capacity of machine is available. From fractional horsepower to 10 megawatt machines are available, and run essentially as constant speed from 0 to full load speed is frequently dependent. Now, coming to our construction. An induction motor has two main parts. The first one, stator. The second one, rotor. We know the stator is a outer frame that is stationary. A stationary rotor, consisting of a steel frame that supports a hollow cylindrical core. We know the outer frame is the hollow cylindrical core. The core constructed from stacked laminations, number of laminations and the number of stampings are bunched together to form a laminated iron core with the laminations. This is outer frame. The next one is rotor. The rotor is inner one, which is going to rotate. It is composed of punched laminations stacked to create a series of rotor slots, providing space for a rotor winding. We have two kind of rotors. Number one, wound rotor. Number two, squirrel cage rotor. You have two kind of rotor: squirrel cage rotor and wound rotor or slip ring rotor. So, depend upon the rotor construction, we have two kind of induction motors: the squirrel cage induction motors and wound rotor induction motor, that is slip ring induction motor. The slip ring induction motor, which is a conventional three-phase windings made up of insulated wire, similar to the winding on the stator. We know the stator, we have a three-phase winding is provided in the stator. Similarly, the winding is provided for your wound rotor induction motor, but the aluminum bus bars is provided for your squirrel cage induction motor. Instead of copper wire, we are using aluminum bus bars or copper bars, which is placed in the rotor slots and bolted or shorted themselves with the help of aluminum rings. So the two, we now see this two construction. Number one, squirrel cage. Number two, slip rings. The advantage of slip ring in our slip ring and rotor is we can add external resistance through the slip rings. But for your squirrel cage induction motor, we cannot add any external resistance because both ends are shorted themselves with the help of end rings. See this simple diagram. The cutaway in a typical wound rotor induction motor, which notice the brushes and slip rings also. So according to this construction, the outer frame is stator, the inner rotating part is rotor. Rotating part we have two kind of rotors. The next one, principle. Before going to understand the principle, we should understand rotating magnetic field. The rotating magnetic field only responsible for the rotor rotation. If our supply is given to our stator, outer frame, the rotor is going to rotate. Now, if the three-phase supply is given to the stator, a three-phase supply is each phase is 120-degree displacement. The three-phase supply is given which produce rotating magnetic field which rotates in the air gap at constant speed, clockwise direction. Speed is 120 F by P. That is synchronous speed, constant speed. Which is rotating in the air gap. Rotating in the air gap. Now, the rotor is stationary. Rotor is stationary. Now, because of this stator flux rotating in the air gap, our which sweeps past over the surface of the rotor conductors, which touches the rotor conductors. According to the Faraday's laws of electromagnetic induction, one EMF induced for your rotor conductors. Now already we see, I told our field is rotating nature. We can see this diagram says our field is rotating nature. And also it is rotating in clockwise direction and constant magnitude. And also one more important point is our resultant field is rotating at the speed of 50 Hz or synchronous speed. Why? Our alternating cycle, each cycle completes one cycle, a fundamental flux completes one cycle. At the same time, our resultant flux also completes one cycle. So already I told the rotating magnetic field cuts the rotor windings and produces an induced voltage in the rotor windings. EMF induced according to the Faraday's laws of electromagnetic induction. Due to the fact that the rotor windings are short circuited for both the squirrel cage rotor and wound rotor also, and which induce the current. This current flows in the rotor windings, which produce one flux. This rotor current produces another flux, that is rotating one more field. This field will oppose the main field according to the Lenz law. Lenz law says such as to oppose the cause producing it. Oppose the main field. So due to the interaction of the two, fluxes. Our resultant rotor starts rotate in the clockwise direction. Now the next question will be arises. Can the induction motor run at the synchronous speed? Now our stator flux is rotating clockwise in the direction, clockwise direction at the synchronous speed. The speed already found, n is equal to 120 f by p. Now the question is arises, can the induction motor runs at the synchronous speed? Answer is no. Now why? The question, next question will be arises, why? If the rotor runs at the synchronous speed, which is the same speed of the rotating magnetic field. Already rotating magnetic field is rotating at the speed of synchronous speed. Now, if the rotor runs at the synchronous speed, which is the same speed of the rotating magnetic field, then the rotor will appear stationary to the rotating magnetic. Both rotor field and stator field is rotating in the same speed. Then the rotor will appear stationary to the rotating magnetic field, and the rotating magnetic field will not cut the stator, which is the main reason for this rotation. Our rotor is rotates. The stator flux cuts the rotor windings. Our EMF induced for your rotor windings. If the rotor field also rotates at the constant speed, that means our synchronous speed, which is will appear stationary. So the no induced EMF will flow in the rotor, and no rotor magnetic flux will be produced. So no torque is generated, and rotor torque will fall below the synchronous speed. That means no induced EMF, no flux. That means no interaction of, not possible to interaction of these two flux, not possible to produce the torque. That's why this is not possible. That means the induction rotor cannot catch the synchronous speed, never catches the synchronous speed. When the speed falls, rotating magnetic field will cut the rotor windings and the torque is produced. So if the speed difference will exist, our rotating magnetic field will cut the state rotor conductors and the torque will produce. So now the next question, the induction motor will always runs at a speed lower than the synchronous speed. Previously we discussed. Now some difference in speed will exist between synchronous speed of the stator flux and the rotor. So the difference between the motor speed and the synchronous speed is called the slip. So slip is nothing but difference between synchronous speed and running speed. Now the formula says slip is equal to, see, this is slip speed. Slip speed is difference between synchronous speed and the motor speed. Now using this formula, we can find our slip. Synchronous speed of the stator flux minus rotor running speed divided by the synchronous speed. Multiplied by 100, we can find the percentage, where S is the slip. If the rotor runs at synchronous speed, what happens? Slip is equal to 0. That means both speed is equal, this 0. The rotor is stationary, slip is equal to 1. Slip is equal to 1. The slip may be expressed as a percentage by multiplying the above equation by 100. Already I told. Multiplied by 100, we can find the percentage. Notice that the slip is the ratio and doesn't have units. So the simple. So now our rotating magnetic field only responsible for the rotation of the rotor. So the first main objective is, we were discussed in detail the construction, and our second objective is principle of operation. So our construction says we have two kind of induction motors. Two kind of induction motors. Our principle of operation says our rotor always rotates less than the synchronous speed. Less than the synchronous speed. So the rotating magnetic field is responsible for this rotation. So the principle of operation is Faraday's laws of electromagnetic induction. Okay. Now in this class we will clearly understand the constructional details and the principle of operation. Thank you so much.